So it's just about priorities. Okay, so we need to keep going. I will keep repeating the same things just in case. Oh, I just opened a parenthesis here. The office hours starting from now, I will be sitting outside of this building because my office has too much dust and I'm very allergic to dust. So I will be sitting there 1 p.m. starting from Tuesday. Tuesday we have class. First day of course we don't have class. So I just want to take 1 minute, not even 1 minute, to talk about the pendulum. So if there is no friction, you see, it's like a perpetual motion, right? It's gonna swing back and forth. So the time it takes to go forward, backward, that will be called a period. So it's the time for one cycle. And what I want you to see is that the energy here, it's going to swing back and forth between kinetic and potential. So when it's going to be, okay, let's stop that. So here it will have no kinetic energy, and all is in potential energy. How do I find the potential energy? You need to find the height, mgh. So you can decide that when the bulb here it's at the minimum position, potential energy equals 0. And then when it's at the maximum position, it's going to be mgh. So here you have maximum potential energy. Then it's going to go through. It's hard to stop it right. Okay, so potential energy is maximum. All that potential energy is turned into kinetic energy. So you have mgh equals 0.5 mv squared, and you can find the speed here. Okay, so it's swinging back and forth between kinetic and potential. But what I want you to see again is that the total amount of energy, which is called the mechanical energy, kinetic plus potential, stays the same. Now, if you add friction, of course, there is no such thing as perpetual motion. So now some energy will be lost to heat, to thermal energy. Okay, so you are losing, you're going to lose some energy. So you can say that the total energy that you start with minus whatever is gone to friction equals the final amount of energy. And then maybe you have done this lab. There is a very simple relationship between the length of the pendulum and the time it takes for one cycle. Okay, so if you have you increase the length, you're gonna increase the time it takes to go back and forth. Okay, it's just a parenthesis. And then where were we? And, is that the right? I don't think this is the right unit. I think we are here. Okay. So we did all that, and you did very well for the last pop quiz, so that was great. Just so just a small parenthesis here. So let's say you have the Earth like a planet. Okay, so it has a huge mass. Okay, and it has a radius r, and you have a small mass here. So if you are not too far away from the Earth, the potential energy, so that will be the gravitational potential energy relative to the ground, is very simple. It's just mgh. Okay, so you double the height, you double the potential energy. So that's an approximation. And remember the force between the two masses, remember, it's from Newton gravitational law. It's going to be equals to a constant, the mass of that mass here, the mass of the Earth, and then the distance between the two masses, which is the radius of the Earth square. We've seen that, right? It's called the inverse square law. That constant here, so that will be the weight. the gravitational weight, the pull from gravity, and that constant here is actually very small. It's 6.67 times 10 to the negative 11, and then you have a whole unit here, but it's in your equation sheet. By the way, before the final, make sure you get used to the equation sheets. Make sure you find all the equations that you need. So anyway, now this is just an approximation. Now, if you have a mass, right, as it's going to move away from Earth, does that make sense that it's going to lose potential energy, right? Because farther and farther and farther away, gravity will get weaker and weaker and weaker, right? So at a given distance, r, okay, the potential energy, the gravitational potential energy, first of all, it's going to be negative. Why is it negative? Because potential energy it's going to be something that wants to bind things together. That means if you want to escape potential energy, you have to put energy in. So it's like it's trapped. It's like we call that an energy well. So that's why it's negative, but that doesn't matter. So G, and that will be the mass of the Earth, the mass of your spaceship. I watched Star. I saw, yeah. The Starship. So I was watching on live and I said, oh, I have to tell everyone. So over the distance R. Okay? So what does it mean? If you move away from the Earth, the potential energy, okay, it's going to decrease. Does it make sense? Because you have less glue. Agree? Mm-hmm. So on Earth, let's say it's on Earth. Now, if I want to use this equation, okay, how much glue there is, okay, that will be the potential energy. It's going to be minus the mass of the Earth, the little mass divided by r, the radius of the Earth. So let me ask you something. If you want to, let's think about Starship. If you want to escape that glue, what is it that you need? Yeah, a force, and the force will provide what? A velocity, right? A change in velocity, an acceleration, right? And what kind of energy is that? Kinetic energy. So you need enough kinetic energy to balance out the potential energy, the glue. You need enough energy to escape Earth, which means on Earth, your mechanical energy equals the gravitational potential that glue you. It's like a glue, you are trapped. But if you put enough kinetic energy, right, then, so that's before, so that will be the energy before, then really far away, okay, it will gonna be equals to 0. They're gonna balance each other. First, you give it a little bit kinetic energy. That's not enough to kill that. More kinetic energy, not enough. More, not enough. And at some point, they will be equal to each other. So you're going to have enough kinetic energy to overcome that glue the starship to Earth. And you see, it doesn't matter on the mass. And you can isolate V. Okay, so that's going to be equals to 2gm over r. Okay, you have it here. You have the equation here. So this is called the escape speed. So it means what is the speed that a starship needs to escape Earth? So for Elon Musk Starship, it's called, it didn't escape. It did have kinetic energy, just enough to get to an orbit, and then it came back. But if you want to escape, go to Mars, because at the end that's what he wants to do. I don't know why going to Mars. I don't see the point. But that's another story. Then you need enough kinetic energy, enough speed to escape. Does that make sense? So if you do the computation, so you have a 2 here. G is the constant that involves gravity, and you see it's a very small constant. It's going to be 0.0000000 because gravity is so weak. You see, I can defy gravity. It's very easy to defy gravity. So it's that constant. It means whoever created the world decided that gravity has to be very, very, very weak so we can stand upright. Otherwise, we will be crawling on the ground. And that will be very dirty, right? We don't want that. But you can build another universe and you can make that constant larger, and then people will not be able to stand up. So it's like a tune. You are tuning. And then that will be the mass of the Earth, the radius of the Earth. For any planet, you can do the same computation. Any planet, Jupiter, Pluto, because I say Pluto is a planet, you can find, or asteroid, or any object, you can find how much speed do you need to escape that planet or asteroid or comet or whatever. Is that clear? Mhm. And now on if you do the computation, you're gonna have 11 kilometer per second. Now, if you convert that, it will be 7 miles per second, which is quite a lot. Now, I know most of you are in chemistry, for example, and in chemistry, you learn that in an atom, electrons are on energy levels, right? And they are bound to the nucleus. They cannot escape. They are trapped. And they can be on that energy level. That will be the ground one, maybe on this one. And then, so the first one is big, and then it gets smaller like this. But anyway, so electron, if you give it enough energy, can make it to this one. Another energy can make back to that one, but it's trapped inside the well. It's like a well, right? So it has negative potential energy here. And if you want the electron to escape, you have to give it enough energy so it can make it to freedom. Or maybe it's here, the electron, and you give it enough energy to escape the well. So that will be called the ionization. You want to ionize. So if you want to ionize, if you want to free the electron, you have to balance out that negative potential energy. Is that clear? So how we do that? For example, we could give it light. If we give it the right light with the right frequency, it will take the energy, get high, escape, and burp out the light in a way. Okay, any question? So that's going to be important for the pop quiz. So this is a book if you are interested, even in biology, if you are interested in it's there is no math in very little math, but you learn a lot. It's called Physics for Future Presidents. Or easier book to read, Physics Behind the Headline. It's by the same author, Professor Müller. And this is very interesting because it's comparing energy. So, and listen up because it's on the pop quiz. Energy of different systems for the same amount of mass, And they compare that to TNT. Okay, TNT. That's what they use in missiles, for example. TNT. Like there was a missile recently launched by Russia, and then it had like 100 kilogram of TNT, just to give you an idea what it's used for. So explosive. So that will be 1 mass of TNT. So all them have the same amount of energy, and we compare to TNT. Now I want you to compare TNT and chocolate cookies. For the same mass, you take a mass of TNT, the same mass of cookies. Which one has the more energy? Cookies. Isn't that surprising? You have 8 times more energy than in the same mass of TNT. And energy is energy. There is no nice energy and bad energy. Energy is joules, it's just energy. So let me ask you something. If you eat that amount of cookies, right? The same that will give you 8 times more energy than TNT. How come there is no explosion? How come for the same mass of TNT there will be a big explosion? It will destroy, but not if you eat the same amount of cookies. Huh? Chemistry? So yeah, so what about chemistry? Difference in what? No, something with the bonds, something with. So it's the same amount of it's the same joules. It doesn't matter if it's chemistry joules or it's the same chemical. It's not the same, but it's also chemical potential energy. So very good. Very good. The time it takes to release energy. So even though 8 cookies, I mean no, the cookies for the same amount of mass, the same mass of TNT of cookies, the cookies will have 8 times more joules, 8 times more calories. However, the time to be released will be larger. And if you remember, there is a trade-off between force and time. Remember that for the final, larger is the time of impact, smaller is the force of impact. It's a trade-off. So even though they have more energy, the time of release will be slower. It's called the metabolism. Otherwise, it will be very bad if we eat. Maybe it will be very good. It's for motivation not to eat cookies. So that's interesting. Yeah, you eat a cookie and boom, and that would be interesting. Fossil fuel, also very impressive. Fossil fuel, coal or oil, you have 10 times more energy in fossil fuel than you have in TNT. A lot of energy in fossil fuel. Now people say, oh, we have to go electric. But look, if you go electric, like if you take the kind of battery you have in a Tesla, for example, that will be the same kind of battery that your computer is using, same technology. And you see, there is like 100 times less energy in a battery, electric battery, that you have in TNT, and even less than you have in fuel. Okay, so that's also interesting. I mean, it's cool, who does not like to drive a Tesla, but you have more energy into fossil fuel, in a gasoline. You can just compare the same mass of gasoline and the same mass of a battery that you have in an electric car. You see the ratio. Okay, you have 15 here, and here you have 0.15. So that will be 10 times less energy available. Also interesting here, the asteroid that killed the dinosaurs, you see, has 165 times more energy than TNT for the same mass. Why? Because all was into kinetic energy. Kinetic energy, change in kinetic energy equals force times distance. The asteroid doesn't go into the Earth too much. That will mean a huge force, right? It's ruin your whole day to have an asteroid hitting the Earth.
What if it explodes over here,
Just before hitting. So it will. So first it will start to vaporize. So it will, but whatever is left is going to hit the Earth, and then the Earth will come to a boil. So it will be very hot. You will have fire everywhere. You have tsunami everywhere. You have earthquakes everywhere. I mean, it will be very bad. You will have what is called a nuclear winter, because all that dust goes into the atmosphere. It will block the sun. The plant cannot grow. The plant eater, the vegan, won't be able to eat. That will be very bad. And then the plant eater won't eat here. So that's ruining your whole day.
It's called landslide, right?
The what?
The asteroid landslide or something.
Oh yeah. It went in the Mexico Peninsula. Yes. You have a great culture. Yes, that's true. next to Mexico. Oh, forget about Florida. Okay, I have for those who are interested, I can show you a simulation. Will be very bad for us. So the one that killed the dinosaur, it was like 10 kilometers in size. So it happens like every 100 million years. We don't want that to happen tomorrow, of course.
Last time it ended Cretaceous 65 million years.
Yes, 65 million years ago. I don't know where is the.
There you go. Bottom tsunami times.
Oh yeah, thank you. Okay, so you see here Mexico. Where's Mexico? Here you have the Gulf, and there the asteroid hit. Oh, not Mexico. Here, yeah, Mexico is here. Oh, that's Florida. Oh, can you see Florida? It's gone. There is no more Florida. So it was a huge tsunami all over. Oh, it's getting even worse here. There was no more Florida at that point.
I don't think there will.
Yeah. So you don't want that to happen. So it was 100 million megaton of TNT. So that will be 100 million thermonuclear weapon. Terrible, terrible. And that's what a thermonuclear weapon can do. So that will be 15 kiloton of TNT. That was Hiroshima. So it's wiped out everything. Well, okay, I'm taking a tangent. Let's go back to physics. Sorry. Okay. So let's define a new, uh, maybe you already know that physical quantity. So it's a new physical quantity. So I highly recommend, like for any class that you take, you have like your notes and you divide in two. On the left, you have the physical quantity, the name, the notation, and then the units. And then on the right, you have all the equations involved with this physical quantity. And the same for chemistry and biology and anything. You need to have like cards so you don't um, uh, uh, forget. So new physical quantity is the average power. The unit is watt. So it's named after James Watt. And it means joule per second. So what is power? It has to do with metabolism. So it's a rate at which energy is produced or consumed. How fast? So that will be the difference between Ferrari, for example, and a Hyundai Venue. So Hyundai Venue is 100 horsepower. Horsepower is another unit for power. So 100 horsepower for a stupid Venue, which is the car I have. And a Ferrari will be like 800 horsepower. What does that mean? It means it's going to consume gasoline 800 times faster. So, of course, it's going to have this punch, oomph, right? So that's power.
You're
Yes. Yeah. Oh, yes. And it's consumes. But who cares, right? It's a Ferrari. Or Lamborghini, same thing. So it will be the amount of, so remember, work is energy in transfer. So how much work, okay, per unit second. So it's like metabolism. That will be the definition of power. So let me ask you something to make sure you understand. We have me, I have a mass m, and you, and let's say we both have the same mass. And we go up the stairs up to the third floor. Okay, so we have the same mass, we go to the third floor. But I'm very slow and you are very fast. So you get to the third floor before me. First question. As you go up the stairs, you are moving at a constant speed. You are doing work against gravity. So what will be the energy that you are spending? So when you go up, what kind of energy you are getting? Potential. Are we using both the same amount of energy? Yes, because we have the same mass and we go to the same height, mgh. However, what's going to be the difference?
The time.
The time. So it will be the power. So we will be doing the same work against gravity, mgh, but your power will be like if you take half the time, your power will be twice. So power is a rate. It's a metabolism. So when you are young, you have a high metabolism, you're going to burn the fuel quicker, you're going to burn the fat quicker, and you have more power. Now, as you get older, we have something called insulin resistance because you are in biology. I'm sure you know about it. That's something very sad happening. The metabolism goes very slow. You don't have enough insulins and your power goes collapses, right? It's all about power. Okay, so let's do something easy. Let's do this one. Very easy. Everyone, you do it. So that way we can review for the final at the same time. So for the final, you're gonna have more of the things that we are doing now. Yeah, conservation of energy, of course, you're gonna have. So the average power is the work over the time. So the unit here is joules. The unit here is in second. And the unit here is in watts. Joules per second. 8,000, right? So the power will be how much energy is used over the time elapsed, which is 5. So it will be 8,000 watts. Okay? So here are some example. How much energy you are using per second, how fast you are burning the fat. Because actually we are burning fat. Running, 1340 watts, skiing, sleeping. Look, I sleep and you are still using some energy. Not much, but not bad. So it turns out that on average, so it depends on your metabolism, but we behave like 100-watt light bulb. Especially before the light bulb, incandescent light bulb were phased out, you will go to a hardware store, you will buy 100-watt, 40-watt, 60-watt. So we are like 100-watt. And remember, joules doesn't care if it comes from a human or an object, right? Joules is joules. So that means we are burning about 100 joules per second, like a light bulb, 100 watts. Same amount of energy per second, we burn exactly the same amount of energy as a light bulb. So let me ask you something. How come if I touch you, I'm not going to burn myself, but if I touch a 100-watt light bulb, it's... Yeah? You all agree about that? Because the same amount of energy will be spread out over a larger area, right? So area does matter. So even though it's the same amount of energy, the area is larger, so you're not going to... So elephant, for example, it's very hot where they live, so they have a very large area. They increase the area with their ears, right? So they can get rid of the heat quicker by increasing the area, right? Okay, so let's answer this question, right? So everyone does that. You're right. So if we are like 100-watt light bulb, okay, so in 1 second we use 100 joules coming from fats, I guess. So in one day, so in one day you have 24 hours and 3600 second in 1 hour. Is that right? Is that right? So it's gonna be you multiply by 100, so 24 times 3600 times 100 joules. Yes. So it means joule is a small unit, right? So um, it, so we have another unit for energy. You have calories, but you have two kinds of calories. You have the chemistry, the one that you use for chemistry, which is lowercase, which is about 4 joules. And because they don't want people to freak out when they buy cookies, they come up with the food calories, try to trick people, and beware that a food calorie is with a uppercase, and this is 1000 little calorie, which is about 4000 joules. Okay, so when you eat a 150 calorie cookies, that will mean 150 thousand little calorie, and then you multiply by 4000. Isn't that terrible? Do I go too fast? No. It's good. So you have one food calorie is for about 4000 joules. So that much of joules, how much is that in calorie? 2000 something? Huh? 2065 food calorie. And don't they tell you when you take a biology class or whatever, don't they tell you that on average you need about 2000 food calorie per day? It comes from that. That makes sense. So if you are an athlete, for example, you have to drink like 3000 or 5000 food calorie. But then they say if you want to lose weight, yeah, you have to go down to 1500 food calorie per day. Now, say it's not true to say that calories in equals calories out because it depends on the metabolism. So human body is not a machine, so it doesn't work like a car. It's not like fuel in equals fuel out. If you have insulin resistance, calorie in, calorie out does not work. Sadly, there is a lot of energy in food. Makes me very sad. Here, examples from the everyday life. If you want to power a small house, you know, the rate at which energy is being burned is about 1 kilowatt. So you need 1 kilowatt, 1000 joules per second for a small house. Okay? We can do 1 horsepower, but for a short time. Incandescent light or human will be 100 watts. Flashlight, 1 watt. A small car like a Venue will be 100 watts. A Ferrari or a Bentley or those kind of car, like 600 to 800 times more power. And then if you want to power a small town, you need that much of watts. So mega means a million. So 1 megawatt, 1 gigawatt for a big city. And this is for the world. So when they say you can power everything with the sun, that's not true. Because the energy from the sun, if you live on the equator, right? So the rays come almost parallel and hit the ground, perpendicular to the ground. So if there is no loss, and if your solar panel is 100% efficient, you will get for 1 meter per 1 meter square, you get only 1000 watts. Okay, you can power a small house. That's it. You cannot power a whole city. Just have to be realistic.
It's also different from like
Huh?
the sun, different from the moon.
Yes, plus, yes, there is a
It's tilted.
an angle. Exactly. So that I'm gonna leave that for the pop quiz. Okay, so let's talk money because it's important to to have a budget, to know if you have enough money to pay for the AC, or if you rent a house. Like if you rent a house to someone, you want to make sure find how much the AC is gonna cost. So the electric company, they're gonna use a different unit. So far we have seen that energy in joule will be equals to hour, so the rate, it's a rate, in watt times the time in second. But the electric company use a different unit. And that unit is going to be the very good, kilowatt hour, very good. And you have to pay attention to that. When you buy a new fridge or oven, you have to do your computation. How long you're gonna keep it? Is it worth it to pay the extra money because it's more efficient, it has less power. So larger the power, more energy hungry it's gonna be. Okay, it's gonna use a lot of energy. Of course, you're gonna pay a higher bill. So it's a balance. So power in that case will be in what? Very good, kilowatt. And time will be in hour. And remember that 1000 watts equals 1 kilowatt. So let's take an example. This one is easy. And the price for kilowatt hour is also a consideration of where you want to live. In Miami, it's very low. In Hawaii, it's very high. In Alaska, it's very high. In New York, it's very high. It depends on the state. Each place in the US has a different price. So let's say this is not happening 10 cents. I think Miami is like 14 cents, but let's say 10 cents. You buy a microwave, 800 watts. So when you buy a microwave or a fridge, oven, it will say, what's the watt? How fast it's going to burn your money. So can you do the computation? So power is 800 watts. You have to convert that to kilowatt. Okay, so you divide by 1000. From watt to kilo, you divide by 1000. Okay, so you're gonna have the energy in kilowatt hour will be power in kilowatt. That's gonna be 0.8 times 2. Is that right? So it will be 1.6 kilowatt hour. 10 cents. So you have, yes, so 10 cents for 1 kilowatt hour. So if you have 1.6 kilowatt hour, question mark. So how much you gonna pay? Do you all agree? You cross multiply, divide. So 60 cents. Okay, so last year, like people don't know cents and dollars. So in $1 you have 100 cents. Just to make sure we are on the same page. Right? 100 cents for $1. Any question? I don't go too fast. You're good? Okay, let's try to do this on your own. Okay, so that way you can plan ahead if you get an AC or if someone rent a room in your apartment, something like this, you want to know how much you need to charge that person for the AC, because AC here is super expensive, especially if you have to run it like 24 hours a day when it's hot, and plus it's humid, so you need the AC. So it's a typical AC, but it's a big one. This one is for a very, very large room. Okay, I'm gonna do. So the power is already in kilo, so that's good. Then we need to find the time in hours. So we have 3 hours per day, so that's good. But then you need to multiply by 30 days for 1 month. I don't know why will you want only 3 hours per day. So that will be 90 hours. Is that right?
Yeah. Yes.
Okay, so the energy in kilowatt hour will be equals to 15 times 90. So that's going to be 1350. So 1350 kilowatt hour. All agree?
Yeah.
Okay. And then you pay 11 cents. So 11 cents for 1 kilowatt hour. Students get really good when it comes to money. Yeah. So you do yeah, you multiply and in dollars. So you divide by 100. 148.5. Yes. So like AC is this one is really big. Okay, usually for a small room it will be smaller AC, but it's worth it to do those computations so you can save money. It's very expensive. AC is very expensive because it has a motor, and everything with a motor working like dryer and washing machine that consume a lot of energy. Compressor, yes, 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 expensive too. I mean, if you can live without AC, you're gonna save money.
Not in Miami.
Some people can, I don't know. So just lay out the equation for this one. Okay, Miami is 14 cents per kilowatt hour, which is not much. Hawaii is like 24 cents, something like this. New York, 20 cents. Alaska is even worse. I think Alaska and Hawaii, they are the worst. Here we good because the energy comes from nuclear, which is cheaper. Okay, so the power will be, you have to divide by 1,000, so 0.1 kilowatt. Agree? The time will be 30 days times 24.
That's 20.
How much is that?
720.
720. Thank you. hours. So energy in kilowatt hour will be 72. And then you multiply by 40 cents. So how much is that?
$10.08.
$10. So 10.08. Thank you. See, I make fun of students, but I'm doing the same thing. Yes. Okay, so that's convenient to know that. And then just a parenthesis here, during the Industrial Revolution, they introduced the horsepower, which is also a unit for power. Why? Because they were trying to switch from horses to automobiles. So they were trying to convince people to buy cars, and that will be more efficient than just going around on horses. So they compare power delivered by horses and power delivered by car. Okay, so that's how the horsepower came to be. So what's one horsepower? That means that a horse can lift like 330 pounds over 100 foot. So if a horse was to pull something, like to lift something like this, like I don't know how to make a horse.
The long body.
Okay, this is my horse, and this is the load. Okay, and the load is 330 pounds. So he's doing work against gravity, and this is 100 foot. So he will be able to lift 330 pounds over 100 feet per minute. So this is your horsepower. Okay, so it's the rate at which energy is produced. Now, if you convert one horsepower is about 746 watts or 1 kilowatt. Okay, and they did that trying to convince people, forget about your horses, switch to cars. But at least they were not eating their horses. In France they used to eat horses for a long time. In Italy too. Like the baby horse is like a delicacy in Italy. But that's a tangent, sorry. So we a horse can deliver a lot of energy during a small time, and usually we can deliver only 4/7 horsepower. We can do 1 horsepower, but only during a very short time. Okay, and there is another equation. If you want to check your equation sheet, you can check that. Another equation can be useful. So if you do power, the average power is work over time. And remember, work is energy in transfer. The definition for work is force times displacement. And we suppose the force is parallel to the displacement. Otherwise, we take the component parallel to the displacement. So work is force divided by displacement. And what is displacement divided by the time? Velocity. So we have another equation for power. Sometimes it will be easier to use this one, where you have the power delivered by a force. Okay, so if you have a force and times the velocity of the object acted upon by that force. So if you have an object with a given velocity and there is a force here, that will be the equation that you want to use. So I'm going to give you an example. An equation. Example, you have an elevator And let's say the elevator is moving at a constant speed. So let's review for the final also. You see you have the lift. So that will be a tension from the cable here. So you have a lift here, the tension. Then here you have what? What is mg? The weight. Very good. And what could that be? What can make it go slower? No, a force. What is the force that make things go slower because the friction, the kinetic friction. And remember, kinetic friction is always along the path. So because those elevator, they are not free to move. Okay? Otherwise, it would be very scary if she's swinging back and forth. And like especially those kids that cannot be controlled and they start to push and then start to swing, that will be very bad. So they are on rails here. Okay. So they are guided and because they are on rails here, you have some rubbing, so you have kinetic friction. So what can I say? If it's moving at a constant speed, there is no acceleration. So what is the equation that I can use? If I want to find t, I can say what? What equals what?
Equals down.
Up equals down. Very good. And you can find t. So let's find t to begin with. It's an equilibrium, but it's a dynamic equilibrium. So it's not at rest. It's moving at a constant speed. So there is no acceleration, which means there is no net force, which means up equals down. Let's compute t. So what is given to us? Okay, you have to be careful. The load. So you have the elevator, which is 1,000 kilogram, but you also have a load of 800 kilogram. So the maximum mass will be 1,800 kilogram. Agree? Okay, because you want to make sure to have enough lift, otherwise the thing's gonna break and they're gonna sue you. Friction, kinetic friction is always along the motion, and it's given to you. It's 4,000 Newton, and they want you to find T. And you want to use everything up equals everything down. Okay, so the weight, remember, weight is mg, right? So it's 18,123 Newton. Do you all agree? Mm-hmm. Right? So what is up? T equals down plus 4,000. So we are reviewing. Make sure I'm not doing any mistake because it happens. 2,000? 22. Thank you. The math what? Because they say this one is 1,000 kilogram, the cage, and the maximum people. Agree? So the one that is doing the work is the lift here, is the tension, because you have a motor here, and that will have to deliver the power. Okay, it's going to consume electricity at a given rate. So we want to find the power, okay, delivered by the lift T, which is the power delivered by your motor here. Here you have a motor, you have an electric motor. And we can use the equation. Average power is work divided by time, which is the force T divided by the displacement. I don't know, I can call that displacement delta Y over T, and that will be the speed. So the power delivered by the tension is B. The tension times the speed. And that's how this equation is used. And the speed is given. It's 3. Exactly. So the power will be 22 times 3, right? Watts, which is 66,000 watts, which is 60 kilowatt. And then you can do the computation, how much is going to cost, the company, if it's, I don't know, running so many hours per day. Okay? Oh, and the only thing I didn't do is to convert to, so they found this because they used 9.8 instead of 10, and they convert to horsepower. And 1 horsepower is 746 watt. So you divide your watt by 746 and you convert to horsepower. It's still a unit used in engineering today, horsepower. Told you, I don't know, Maserati is like 800 horsepower, all those cars. I'm not sure about the Tesla.
Use
How much horsepower the Tesla?
the fastest one goes over 1,000.
Horsepower?
Yes.
No. Really?
Yep. There's some cars with 2,000 horsepower. The
A Tesla?
Tesla Plaid goes over 2,000, just over 2,000.
Wow.
I mean 1,000. Sorry,
You sure?
it's expensive. It's $250,000 car.
Wow. Okay, 1,000 watt for the more expensive Tesla, if you want. For a gift, right? For the holidays. Uh, so energy units, power units. Okay? Any question? So the test 3 was torques and momentum. So obviously for the final you're gonna have energy. It's cumulative. Oh, yes. Okay, so we're gonna start a new unit, but I'm not going to go deep into it. I'm just gonna touch on it because the next unit is even more interesting. Okay, it won't be mathematical. Okay, it's mostly conceptual. Here it's gonna be a little bit of math, but not that much. And starting from now, it's very easy. You pass the challenging part, which was kinematics, right? Kinematics can be challenging because of and the vectors is also challenging. Okay, so far we talked about translation, right? But you also have rotation. We already talked about rotation, about an axis of rotation here. So you see, let's say he's spinning, there is no friction and he's spinning at a constant rate. You can define the rate of spinning. So it could be, I don't know, 3 revolutions per minute. So that will be called the rotational speed. Okay. So it will be the speed at which it's spinning. So it's called rotational speed. Okay, so it could be like 33, I don't know, like revolution per minute. So, but you see here you have point C and point B. Obviously, do you think they have the same spin? Are they spinning at the same rate? Are you sure? They don't have the same speed. I agree with you. But the rate at which it's spinning. Yes, it takes the same time for the shoulder to go around once than it takes for the arm to go around once. Yes? Otherwise, your shoulder is going to go this way and your you're going to be all deformed. And that will be weird. So no, that's not happening. So all those points, they're going to have the same rate of spinning. However, which point will cover the larger distance? C or B? C. So even though they have the same rate of spinning, we say that this one will have a larger linear speed. Okay, so the speed, so speed meaning distance over time will be larger. Does this make sense? So we're going to define that. And of course, if it's going to spin faster, we're going to have also an acceleration. So this is called rotational motion. So it's going to be kinematics again. Okay, but we won't do in 2D or whatever, so it's much easier. But you have the parallel between linear motion and rotational motion. So it's a nice review as well. So before, remember the first class or the second class, I talked about the position, the location on the number line. And here we're going to talk about the angle. So for example, here, if you have like something that is spinning, you see, can you see? Everyone can see. So it's spinning like this. Okay. So I can decide this is the angle 0, and I'm going to spin to the angle 30. Okay. So that will be called my angular position. Okay. So my angular position will be 30 degrees. So you can use degrees. Usually you use radians. So 360 degrees is 2 pi radians. So 30 degrees is pi over 6. So that will be the angular displacement. So before we talked about the velocity, which was displacement over time. Now we're going to talk about the angular velocity. So for example, if there is no acceleration, so it's going to spin at a constant rate, right? So you can define the number of revolution per minute. So back then, when I was your age, long time ago, we will listen music on those vinyl records, right? The big one, it was 33 revolution per minute. The small one, 45 revolution per minute, right? So that will be a spin. It will be the angular speed, right? So it means in 1 minute, it will go 33 times. Okay? So that's what we call the angular velocity. Now, if I apply a torque, see, I'm applying a torque, I'm going to make it spin faster. So it's going to accelerate. Acceleration will be how fast it's spinning faster. Okay, so you're going to have an acceleration as well. You see, it's a nice symmetry between them. And then you have the same kinematics equation, but now you are replacing V by omega, the rate of spin. Okay, how fast it's spinning. How fast it's spinning is the angular velocity. Instead of having the position, you're going to have the angular position, okay, or displacement. So if you go from 40 degrees to 80 degrees, your angular displacement will be 40 degrees. Then, okay, so that's interesting. Inertia, remember the laziness, the resistance to change the state of motion. For linear motion, it's the mass. But for spinning, it's not only the mass. So imagine you are in, and here's another idea for a demo. You go to Miami to the ice ring, right? And you spin. If you're good at it, you have to be very good at it. You spin. Of course, someone heavier, right? For the same force, is not going to spin as fast. Do you agree? So inertia will depend on the mass, but not only. What's going to happen if you spin and then you bring your arms in?
Go faster now.
Faster. So the laziness, the resistance to spinning, not only depends on the mass, but the distribution of the mass. around the body. So when you bring the arms in, you decrease your inertia, you spin faster, you extend the arm, you're going to spin slower. You can do that experiment if at home, for example, you have a chair that can spin, like the chair that you have for the computer. You have someone sitting on that chair, and he has to have like heavy weight, like 5 pounds both sides, and you spin that person, and that person brings the arm in. That person should spin faster and then slower. You want to make sure that there is not too much friction for that to work, right? So maybe you can put silicone oil, whatever, so it's gonna spin faster, right? And see, that experiment is not hard to do. You want to make sure you lift your feet so it doesn't touch the ground. Bring your arms in and spin faster. So the resistance to spin faster or slower, the inertia, it's called the moment of inertia or angular rotational inertia. It depends not only on the mass, but the distribution of the mass around the axis of rotation. Okay, so here you have the force, F equals ma. Here, remember, what is the physical quantity that makes something spin? It's called the torque. The torque, right? Like a twist. It's like a twist, a torque. So instead of having a force, you have a torque. And the torque, instead of having a mass, you have the moment of inertia, and you have the acceleration, This is very interesting. So you have the momentum, linear momentum, and here you have the angular momentum. Angular momentum will can be changed by torque, the same way as momentum can be changed by force. And you have something called conservation of spin. Example, you take a cat, and you can do that experiment only if you have a relaxed cat. Some cats are not very friendly. But if you have a relaxed cat, you can do that. You hold the cat by its legs. Make sure something is soft, so soft landing, and you let go with your cat. He's gonna do something amazing because cat comes from another planet. They know their physics. He's gonna spin its tail in one direction, and the body will spin in the opposite direction. So he's using conservation of spin. The tail spin in one direction, the body has to spin in the opposite direction, and then he extends its body and he lands safely. Right? So you have something called conservation of spin. Work, same, makes sense also. Work is force times displacement. Remember, I'm reviewing at the same time. The force has to be parallel, so it has the parallel component times the displacement. Work is the torque times the angular displacement. You have kinetic energy here, kinetic energy, power, force times speed, power, torque times speed. Isn't that easy? It's kinematics. Now you have relationship between um, the two physical quantities here. So for example, if something is spinning from A to B, okay, so this is a distance, right? It's a length, it's a linear length because you can take a string and measure it. And the relationship between this angle here and that length is very easy. It's going to be the length equals r times theta. Okay, so it's let me think how to explain. Okay, you can see that. I can show you that in a very simple example. And we're going to take examples that will be easier. So what's the distance around the circle? 2 pi. So the distance around. Okay, so it's you take a string, you go around. You have to go around once, you can go around twice, 3 times. So the distance, I'm going to call it S equals 2 pi r. Do you agree? And what is the angular displacement as you go around? So delta will be what in radians? Yes, as you go only once, it's going to be 2 pi. Do you agree? Or 360 degrees. So we have the distance around equals 2 pi, that will be your displacement, times the radius. And that will work even if you don't take the whole distance around, you just take a little piece here, it's still going to work. Right? Now, if this is spinning, like let me show you something spinning. Is it spinning here? So it has a rate of spin. Okay, so it has a rate of spin, revolutions per minute. And that here, let's say you take this mark here, it has a speed. Okay, so distance over time, a linear speed. So if you divide both sides by the time, you're going to have the speed of a point. So that will be the speed of A. For example, it has a speed, it has a velocity here, V. It's going to be equals to omega times r. And the acceleration will be equals to alpha times r. So we're going to take examples so it will be easier to understand. But that makes sense, right? This is easy to understand. You start from here, you get this one. So any length here will be equals to the radius times that angle here, except this has to be in radians, this has to be in meters, and this is in meters. So if you do S equals theta times R, this one is in meters, radians doesn't count, so this one has to be in meters. Okay. When you say the speed here is how fast point A is moving, and acceleration will be how fast A is getting faster. So example conservation of spin, like just take a tangent again. Let's you know what is that? Matrix. And so it's conservation of spin, because if you do this, your body is going to move in the opposite direction, right? If you are in a swimming pool and you do that, it's very cool. The body is going to rotate in the opposite direction. So when he rotates his arms in this direction, the body is going to rotate in the opposite direction. So this is conservation of spin. Matrix, the first Matrix was amazing. It was a really, really, really good movie. The so let's see. Um, okay, so to understand what I mean by the tangential speed, the linear speed, do they have all the same rate of spinning? Yes, but the velocity, is it the same? No. No. So the one on the edge is going to have a larger velocity because during the same time he will be covering the larger distance. What about the one at the center? Does it have a rate of spin? Spin. Yes, spin, he's spinning. But is he covering any distance? No. Isn't that interesting? So the relationship is the velocity, in this case, equals r, the radius, times the rate of speed. So you didn't know that time. That's my time, and we do terrible things with those vinyl, right? When we were listening to music. So if you had the hamsters, it was so cool to do that. But you see that this one will go twice as fast as that one. Isn't that cute? Like it was really fun to play with those. And then now you can still buy those. My son has a collection of that. They still publish those even for modern music, right? The vinyls, it's still around. You can still buy them. The music is very special. Like if you like music, it's not the same. It's not digital music. It's analog music. So it's not the same. It's a great experience to buy to try. Like especially classical music, it's not the same experience as digital. I love hamsters, so cute. Mhm. Okay, so that's gonna be the same thing. That will be the angular displacement. Okay, so that comes from the book Johnson and Cutnell. I highly recommend that you read the book. Like even if you go to PT school, for example, you can get a doctorate right now. It's not been always this way. Since couple of years, you can get a PhD in PT, a doctorate, right? So you go to graduate school, and but you still need to have physics, right? Physics 1 and physics 2. So make sure you go over your textbook. And I believe it's a great future for PT because given that we are all the time on the computer, breaking our back, it's going to have a lot of jobs. So anyway, that will be the relationship I was telling you about. Blah, blah, blah. Okay, let's try to do this one. So this is the arc. This is called the arc length. Okay, it's a linear length because you can measure it with a string. This is your angular displacement. That will be in rad. You have to put that in radian. Arc length. So what's the equation? So the arc length, which is in meters, equals the radius r times the angle here, but it has to be in radians. And you have to convert 2 degrees in radians. So for example, you can say, okay, 180 degrees is pi radians. So 2 degrees is question mark. So you cross, multiply, divide. Is that right? So pi, so you have pi here times 2, enter, divide by 180. Make sure I'm not doing any mistake. Okay. So that will be the angle in radians. Agree? I didn't lose anyone. Times the radius. Okay, so we are reviewing scientific notation. So times 4.23 times 10 to the 7. Did you get that? 1, 2, 3, 4, 5, 6. So 1.5. 1.5. 6 millions. Do you all agree? Okay. Okay. 1.5 times 10 to the 6 meters, which is about 920 miles. Okay, so that's not that hard. Okay, so same thing for the angular velocity is the angle over the time. That will be in radians and that will be in seconds. So let's try to do this one and then I will open the pop quiz. So again, the speed is radians per second. It could be in revolution per minute in engineering, but here they say radians per second. It could be degrees per second, RPM, but now we want radians per second. And that's from your book. It's a very nice book. Johnson and Catnell, highly recommended. So velocity equals over time. So two revolutions. So one revolution is what in radian? 2 pi. Okay, okay, or 360 degrees. So two revolution will be 4 pi in radians. So that will be 4 pi divided by 1.9. 6 point. Do you all agree? You know how to do it? 6.6 rad per second. So 4 times 3.14, you can, pi is a 3.14, whatever, divided by 1.9, 6.6. Okay? Oh, the only thing I forgot is that a spin is actually like a vector, so it could be positive or negative. So if it's spinning clockwise, it's going to be negative by convention. Counterclockwise is going to be positive. So how do we define the vector? You take your hand, you all have a right hand here. If it's spin this way, the thumb, you have a thumb, goes into the screen, that will be the direction of the vector. So omega, we are not going into it, so don't worry about it, but omega is a vector. In that case, it's going into the screen. Oh, that's what it says here. You see, if it's spinning this way, omega is like a vector, will be your thumb. Here, if it's spinning the other way, it's going to be down. Any question? And then we have acceleration. We'll do a few problems and we'll move to the next unit. You see, you recognize it's the same equations.